A gas-insulated substation GIS is a high-voltage substation in which the major conducting structures are contained within a sealed environment with a dielectric gas known as SF6, or sulfur hexafluoride gas as the insulating medium. In comparison, a conventional AIS or air-insulated substation, atmospheric air is the dielectric gas medium, as these types of substations are almost always located at outdoor locations. GIS technology originally began in Japan in the 60s, where there was a critical need to develop substations with a greatly reduced footprint. GIS was slowly adopted by various other countries over the following years. After about 5 years of evaluation and testing, GIS system construction increased to about 20% of new substations in countries with severe space limitations. For countries with space readily available, a higher cost of GIS relative to AIS has limited its adoption to special needs cases. In the US, only about 2 to 5% of new substations are constructed as GIS. With GIS technology, the clearance needed for phase-to-phase or phase-to-ground for all equipment is much less than that of an AIS or air-insulated substation. The total space required for a GIS is roughly a tenth of that needed for a conventional AIS facility. While the conventional AIS requires several feet of air insulation to isolate a conductor, SF6 gas insulation only needs inches, allowing a GIS facility to fit into areas far smaller than that of an AIS facility. A GIS is mainly constructed where real estate space is expensive or scarce. GIS technology is a good choice to use in Arctic or desert locations, as it can be enclosed in a building which is environmentally protected from extreme conditions. In addition to protecting the system components from extreme heat and cold, GIS technology encloses the electrical components within a Faraday cage which shields the system from potential lightning strikes. Each compartment housing the live sections of the GIS system is gas-tight, with respect to one another. This ensures that the gas is not allowed to pass to an adjacent module, as well as ensures that gas monitoring is independent. O-rings are installed at the equipment and enclosure flanges to ensure the gas-tight integrity of the modules. Gas monitoring system. This includes an integrated alarm system, as well as automated tripping and lockout features in case of low-pressure conditions due to leakage. This is critical, as when the pressure of the dielectric gases drop, so does the insulating capability of the SF6 gas. Gas-insulated technology becomes more desirable as the voltage requirements increase. As an example, the footprint of a 765 kV conventional substation is considerably large. A station footprint of this sized station would be significantly less were it to employ GIS. GIS technology can be used for installations in areas where the cost of real estate or the aesthetic appeal and safety is a significant consideration. When acquiring land for a conventional AIS station in some densely populated areas, it can be cost-prohibitive, politically sensitive when eminent domain is required to seize the land, or downright impossible to locate. Imagine attempting to build a high-voltage AIS in urban areas such as downtown New York City. One approach to the expansion of existing AIS is mixed technology switchgear or hybrid GIS. This approach is especially suitable for the expansion of an existing substation without requiring large areas of additional real estate, which is often unavailable. This design uses GIS breakers, switches, and voltage current transformers with interconnections between the breaker positions and connections to other equipment using air-insulated conductors. The construction of an indoor air-insulated substation would be highly impractical and difficult to operate safely. However, a gas-insulated substation can easily go inside an industrial building. It can be incorporated into the electrical infrastructure of an industrial facility, allowing for on-site stepping down of voltage. GIS systems are usually installed on a monolithic concrete pad or directly on the floor of a housing facility. The system is attached by bolting or welding the GIS support frames to embedded steel plates of beams, or by the use of chemical drill anchors. These are not recommended, as the dynamic loading from circuit breaker operations may loosen the expansion anchors over time. Bus expansion joints. Type of expansion joint may be recommended in the large GIS installations. The expansion joints are installed between the various sections of the GIS to adjust to the fit-up in the field. They can also be installed to address thermal expansion of the GIS system. Disadvantages of GIS systems. System cost is higher compared to that of a conventional AIS. Delivery of SF6 gas to the site can be problematic. GIS substations are indoor type, requiring a separate building. System cleaning maintenance are critical to reduce conductive particle contamination. Particle or moisture contamination inside the compartment causes flashovers. Outages can be extremely long, and the damage to the system will normally be severe following a fault condition at a GIS substation. Access to live parts for maintenance is more problematic, and harder to diagnose without gas reclamation and disassembly of the modules. Disadvantages of the conventional AIS system: equipment deteriorates when exposed to ambient atmospheric conditions. Equipment becomes contaminated when exposed to pollutants such as airborne particulate matter. Requires a lot of real estate, which can be expensive to acquire in dense urban areas, may require the use of eminent domain to secure the necessary parcels. Less stable, with reduced safety of operation compared to GIS, in seismic regions. Requires regular maintenance. Requires special consideration in regions with altitudes higher than 3,000 feet mean sea level, due to the lesser density of the dielectric gas atmospheric air. The poor dielectric properties of air, as well as secondary factors such as humidity, pollutants, salt, and moisture means that more space is needed. SF6 gas in GIS substation uses a superior dielectric gas, sulfur hexafluoride SF6, at a moderate pressure for phase-to-phase and phase-to-ground insulation. The high-voltage conductors, circuit breaker interrupters, switches, current transformers, and voltage transformers are totally encapsulated within the grounded metal enclosures surrounded by pressurized SF6 gas. In a GIS, the active components of the system are protected from deterioration due to exposure to atmospheric air, moisture, particulate contamination, etc. This results in a system which is more reliable, requires less maintenance, and will have a longer service life in excess of 40 years than its conventional AIS counterpart. For any one-line diagram there can be several possible physical arrangements. When deciding upon the physical arrangement, the shape of the site for the GIS and the nature of connecting lines and cables should be considerations. Most GIS designs were initially developed for a double-bus, single-break arrangement. This popular approach has good reliability, and is simple to operate. Additionally, it allows for easy protective relaying, excellent economy, and provides a small footprint. The IEEE and the IEC also have standards and technical specifications which cover the design, testing, installation, and use of GIS systems. IEC standards. Additional international standards for GIS are covered under IEC code. The International Electrotechnical Commission, or IEC, is an international standards organization that prepares and publishes international standards for all electrical, electronic, and related technologies. IEC standards cover a variety of technologies from power generation, transmission and distribution to home appliances and office equipment, semiconductors, fiber optics, batteries, solar energy, nanotechnology and marine energy, as well as many others. IEC GIS Standard 62271, 203 High Voltage Switchgear and Control Gear Part 203, Gas Insulated Metal Enclosed Switchgear for rated voltages above 52 kV. Early cost comparisons of GIS projected that, on the basis of a total installed cost, the cost of a GIS would equal the cost of an AIS when the voltage of the substation reached the 345 kV range. As voltages went above the 345 kV threshold, GIS facilities would be the cheaper alternative over AIS. Present-day cost analysis have shown, though, that the cost of AIS has been reduced substantially by advances in technology and manufacturing processes, while GIS equipment has shown no similar reductions in cost. Even though GIS has been a well-established substation technology for a long time, with a proven track record of high reliability, requiring a minimal amount of maintenance, it is still perceived as being too costly and only applicable to special needs cases where space is the primary deciding factor. Currently, the cost of GIS costs is being reduced by integrating certain functions performed among the components of the system. For example, as digital control systems become the norm in substations replacing analog, pricey electromagnetic CTs and VTs of a GIS will eventually be replaced by less expensive sensors such as the optical VTs and the Rogowski coil CTs. These sensors are much smaller, thus reducing the size of the GIS assemblies, allowing more bays of GIS equipment to be shipped turnkey and fully assembled. This allows for lower installation and site development costs, thus the advantages of GIS compared to AIS increase. Sulfur hexafluoride is a non-toxic, inert and non-flammable gas consisting of a sulfur atom surrounded by and tightly bonded to 6 fluorine atoms. Sulfur hexafluoride SF6 is the most common insulation gas in high-voltage technology because of the electron attachment electron affinity. SF6 is around 5 times the density of atmospheric air at mean sea level, and has no color, odor, or taste. SF6 is almost purely water insoluble, and as with all other gases, its solubility decreases as the temperature of the water increases. SF6 gas is enclosed in GIS systems at pressures between 400 to 600 kilopascals absolute. This pressure range is ideal to prevent the gas from condensing into a liquid at the lowest potential temperatures which the equipment may be subjected to. SF6 is a gas in which the speed of sound propagation is about 3 times less than in air, at atmospheric pressure. The sound of the interruption of the arc will thus be quieter in SF6 than in air. SF6 has a 3 times higher dielectric strength at 0.1 MPa/1 atm or atmospheric conditions compared to air. When the pressure within the GIS enclosure increases, so does the dielectric strength of the SF6 gas, due to the increase in density. At pressures such as those within a GIS enclosure, the dielectric strength of the SF6 gas can become much higher than that of atmospheric air. SF6 tends to be roughly 100 times more effective for interrupting arcs than air. SF6 has become the standard for interrupting mediums, used in high-voltage circuit breakers applications, replacing older insulating mediums, composed of oil and air. There are, however, some reactive decomposition byproducts which are formed due to the interaction between the sulfur and fluorine ions with the trace quantities of moisture, air, and other contaminants found in the system environment. These quantities formed are typically minuscule, and molecular sieve absorbance within the GIS enclosure will aid in eliminating these reactive byproducts over time. Hydrofluoric HF acid is a toxic breakdown product of SF6. It is typically a gas, with a boiling point of approximately 19 degrees Celsius. Symptoms of exposure are delayed. Due to its high reactivity, it does not have a long half-life. Sulfur dioxide SO2, a toxic breakdown product of SF6. It is typically a gas boiling point approximately -10 degrees Celsius. Thionyl fluoride SOF2, a toxic breakdown product of SF6. It decomposes over time in the presence of moisture into SO2 and HF. It is a colorless gas with a pungent odor similar to rotten eggs, condensing at approximately -43 degrees Celsius. SF6 gas is usually delivered in 50 kg gas cylinders in a liquid state, at a pressure of roughly 6,000 kilopascals. Gas handling systems include components such as filters, compressors, and vacuum pumps which are commercially available. The best practices and personnel safety considerations for SF6 gas handling are addressed in international standards. SF6 is a strong greenhouse gas that has the potential to seriously contribute to the effects of global warming. At an international treaty conference in Kyoto, Japan in 1997, SF6 was listed as one of the 6 greenhouse gases whose emissions should be reduced. Even though SF6 is a relatively minor contributor to the total amount of greenhouse gases, it has a very long life in the atmosphere, with a half-life which is estimated at 3,200 years. So the effect of even small quantities of SF6 being released into the atmosphere is cumulative and permanent, unlike some other greenhouse pollutants, which are quicker to dissipate. Gas recycling. To control gas leakage from a GIS system, the SF6 is completely contained within the sealed enclosures, allowing for full reclamation and recycling. By following the present international guidelines for use of SF6 in electrical equipment, the contribution of SF6 to global warming can be kept to less than 0.1% over a 100-year period, when guidelines are stringently followed by GIS personnel. The rates of SF6 gas emissions from use of high-voltage electrical equipment have been reduced over time. This is mainly due to utilities adopting better handling and recycling practices. Field checks of GIS in service for many years have shown that the leak rate objective can be as low as 0.1% per year if handling and recycling standards were to be revised. The SF6 gas in the enclosures must be dry enough to prevent condensation of moisture onto the surfaces of the epoxy support insulators, as moisture on the surface can cause a dielectric breakdown. Inside the enclosures will help to reduce the moisture levels in the gas, though over time moisture evolves from the internal surfaces and out of the solid dielectric materials. When the moisture condenses as ice, the breakdown voltage is not affected. Gas dew points. Thus gas dew points should be maintained below approximately -10 degrees Celsius. Additionally, levels below 1000 ppmv of moisture are typically specified, and easily obtainable when careful gas handling is practiced. During the factory and field power frequency high voltage tests, contaminating particles can be detected as they are transported by the electric field, causing small electric discharges and acoustic signals. Removal. Once detected, they can be removed by opening the equipment. Some GIS equipment is outfitted with internal that captures these particles before they relocate where they might cause breakdown. Most GIS assemblies are appropriately shaped to provide low electric field regions, where particles can come to rest without causing breakdowns. Recycling SF6. When severe situations of gas contamination occur, the SF6 manufacturers will take back the contaminated SF6 and reprocess it, in effect turning it back into a new SF6 product. Permanently retiring the gas. Though not yet a common situation, an end-of-life scenario for the eventual retiring of SF6 gas product is the incineration of the SF6 along with materials that will enable it to become part of environmentally acceptable gypsum. There are alternative types of gas to SF6 that exist for medium voltage electric power equipment. However, there are no viable alternatives which have been identified for use in high voltage electric power equipment, in spite of years of painstaking research. The alternatives have shown a number of disadvantages that outweigh any advantage they may have in respect to a lower greenhouse gas effect. Thus, SF6 will continue to be used for GIS where interruption of power system faults and switching is concerned. GIS systems are assembled from standard equipment modules. Types of modules include circuit breakers, current transformers, voltage transformers, disconnect and ground switches, interconnecting bus, surge arresters, connections to the rest of the electric power system. GIS enclosure modules are joined together using bolted flanges which have an O-ring sealing system for the enclosure. The conductors have a sliding plug-in contact for connecting the conductor sections. Cast epoxy support insulators come in types such as post, disc, and cone. Integrity testing. When testing the integrity of support insulators, a high voltage power frequency withstand test with sensitive partial discharge monitoring is used. The electric field stress inside the cast epoxy insulator should be below a certain level to avoid aging of the solid dielectric material. Electrical stress limits on the cast epoxy support insulator component are not a critical constraint of the design, as the dimensions of the GIS are mainly set by the lightning impulse withstand level of the gas gap, and the need for the conductor to have a somewhat large diameter, in order to carry load currents of several thousand amps. The result is enough space between the conductor and enclosure to accommodate support insulators having low electrical stress. Enclosures are normally cast or welded aluminum, although steel is also commonly used. Steel enclosures require painting on the interior and exterior to prevent rusting. Aluminum enclosures don't require painting, but may be painted to improve cleaning, provide a better appearance, or to optimize heat transfer to the ambient atmosphere. Deciding between aluminum and steel is based on the cost differences between the two metals and also on the continuous current. With continuous currents exceeding roughly 2000 amps, steel enclosures will require non-magnetic inserts of stainless steel. Otherwise, the enclosure material should be changed to all stainless steel or aluminum. Earlier single-phase GIS enclosures were single-point grounded to prevent circulating currents from flowing in the enclosures. Presently, the practice is to use multi-point grounding even though this leads to some electrical losses in the enclosures due to circulating currents. 3 enclosures of a single-phase GIS should be bonded together at the ends of the GIS to encourage circulating currents to flow. These circulating enclosure currents act to cancel the magnetic field that would otherwise exist outside the enclosure due to the conductor current. 3-phase GIS enclosures do not have circulating currents, but do have eddy currents in the enclosure, and should also be multi-point grounded. With multi-point grounding and the many resulting parallel paths for the current from an internal fault to flow to the substation ground grid, it is easy to keep the touch and step voltages for a GIS to the safe levels prescribed in IEEE 80. Specifications for pressurized vessels in GIS enclosures are established within GIS standards. The actual design, manufacture, and testing procedures follow the established pressure vessel standard for the country where the equipment is manufactured. Due to the modest pressures involved in GIS enclosures, and the classifying of GIS as electrical equipment, third-party inspections and code stamping of the GIS enclosures are not mandatory requirements. There is typically no need for periodic inspections or maintenance of GIS internal components. Dry inert gas environment. The interior of the enclosure is dry, with an inert gas environment that is not subject to aging. UV exposure. Additionally, there is no exposure of any of the internal materials to sunlight and the damaging effects of UV radiation. Module seal deterioration. The O-ring seals in the modules are normally found to be in exceptional condition, because there is usually a double seal system, with the outer seal protecting the inner seal. GIS modules are typically transported in the largest, most practical assembly size possible for transport, clearance, and maneuvering. The lower voltage units can usually be delivered with 2 or more circuit breaker positions fully assembled. GIS modules are connected to one another, using bolted flanged enclosure joints and conductor contacts. This makes the assembly process proceed fairly quickly. Electrical contacts in GIS systems. There are a variety of designs for the sliding contact element. Generally, the sliding contacts have many individually sprung silver-plated, copper contact fingers working in parallel. Contact lubricants are used to ensure that the sliding contact surfaces do not generate particles or wear out over time. Circuit breakers, both AIS and GIS, use basically the same type of dead tank SF6 puffer circuit breaker. However, with GIS systems, instead of SF6 air bushings mounted on the circuit breaker enclosure, the GIS circuit breaker is directly connected to the adjacent GIS module. Considerations for current transformers. For CTs installed on the inside of the enclosure, they must be shielded from the electric field produced by the high voltage conductor, otherwise high transient voltages can appear on the secondary winding through capacitive coupling. For CTs mounted on the outside of the enclosure itself must have an insulating joint, and enclosure current shunted around the CT. Both of these types of GIS construction are widely used. Voltage transformers. VTs used in GIS applications are the inductive type with an iron core. The VT is usually a sealed unit with a gas barrier insulator. The VT is easily removable, so the GIS can be high voltage tested without damaging the unit. Installation. Option 2. The VT is provided with a disconnect switch or removable conductor link. Primary winding is supported on an insulating plastic film immersed in SF6. Disconnect switches. Components of a disconnect switch includes a moving contact that opens or closes a gap between stationary contacts, when activated by an insulating operating rod, that is moved by a sealed shaft which runs through the enclosure wall. Stationary contacts. These have shields that provide the appropriate electric field distribution to avoid too high a surface electrical stress. Contact operating velocity. The velocity of the moving contacts in a disconnect switch is relatively low in comparison to that of a circuit breaker's moving contacts. The disconnect switch is only able to interrupt low levels of capacitive or small inductive currents. Fast-acting disconnect. For transformer magnetizing current interruption duty, the disconnect switch is provided with a fast-acting spring operating mechanism. Load break disconnect switches. This type of disconnect switch has been used in the past in GIS systems. However, with improvements and cost reductions of circuit breakers, it is no longer practical to continue installing this type, as a circuit breaker should be used instead. Ground switches have a moving contact that opens or closes a gap between the high voltage conductor and the enclosure. Sliding contacts. These electric field shielded contacts are incorporated at the enclosure and the conductor. Maintenance ground switch. This type is operated either manually or by motor drive to close or open in several seconds. Fully closed, it can carry the rated short circuit current for the specified time period 1 or 3 seconds without damage. Testing with the use of shunt ground switches are normally provided with an insulating mount or an insulating bushing for the ground connection. During normal operations, the insulating element is bypassed with a bolted shunt to the GIS enclosure. During installation or maintenance with the ground switch closed, the shunt can be removed, then the ground switch used as a connection between the test equipment and the GIS conductor. Voltage and current testing of the internal parts of the GIS can then be done without removing SF6 gas or opening the enclosure. A typical test would involve the measurement of contact resistance using two ground switches. Air-insulated surge arresters in parallel with the SF6-to-air bushings usually provide adequate protection of the GIS from lightning impulse voltages at a much lower cost than SF6 insulated arresters. With the AIS, there is a significant decrease in withstand voltage for switching surges compared to lightning impulse because the longer time span of the switching surge allows time for the discharge to completely bridge the long insulating distances in air. With the GIS, the short insulation distances can be bridged in the short time span of a lightning impulse, so the longer time span of a switching surge does not significantly decrease the breakdown voltage. Insulation coordination studies usually show there is no need for surge arresters in a GIS. However, many users specify surge arresters at transformers and cable connections as the most conservative approach. When connecting GIS modules which are not directly connected, an SF6 bus that consists of an inner conductor and outer enclosure is used. Ancillary components such as support insulators, sliding electrical contacts and flanged enclosure joints are usually the same as those used for the GIS modules. The length of a section of bus is normally limited to about 6 meters, by the allowable span between the conductor contacts and support insulators. Gilgas insulated transmission lines. There are specialized bus designs which have section lengths of 20 meters that have been developed and are applied to both GIS and separate transmission link applications. SF6-to-air bushings consist of a hollow insulating cylinder which is attached to a flange on the end of a GIS enclosure. This insulating cylinder contains pressurized SF6 gas on the smooth-surfaced interior and can be exposed to atmospheric air on the outside. Moisture and contaminant shields are sheds located on the outside of the bushing. These improve the performance of the bushing in wet or contaminated conditions. Internal metal shields. These help to control electric field distribution. External shields. Higher voltage SF6-to-air bushings also use external shields. Material of insulating cylinder. In the past these were often made of porcelain, but many now are made of a composite consisting of fiberglass epoxy inner cylinder with an external weather shed of silicone rubber. The composite bushing has better contamination resistance and is normally safer than porcelain as it will not fracture. Power cable connections. Testing port. On the gas side, there is a removable link or plug-in contact. This contact transfers current from the cable to the GIS conductor. Testing. For the high voltage testing of the GIS or the cable is disconnected from the GIS by removing the conductor link or plug-in contact. Testing access port. On the GIS enclosure nearby to the cable termination, there is usually an access port. This port can also be used for attaching a test bushing. SF6-to-oil connections. For connecting a GIS conductor directly to a transformer, a special SF6-to-oil bushing that mounts on the transformer is needed. Transformer side. The bushing connection is immersed in oil on the end with the transformer's high voltage leads. SF6 gas side has a removable link or sliding contact for connection to the GIS conductor. The bushing may be an oil paper condenser type or solid insulation type. Because leakage of SF6 into the transformer oil must not occur, most bushings have a center section, allowing SF6 leaks to disperse into the atmosphere rather than the transformer. For testing, the SF6 end of the bushing is disconnected from the GIS conductor after gaining access through an opening in the enclosure. The enclosure of the transformer can also be used for attaching a test bushing. Local control cabinet. In wiring the GIS back to the substation control room, a local control cabinet LCC is usually provided for each circuit breaker position. Shielded multi-conductor control cables are used for the control power wires for operating mechanisms, alarms, heaters, auxiliary switches, CTs, and VTs which are run between the GIS equipment modules and the LCC. Very fast transient voltages. Switching and circuit breaker operations in a GIS produce surge voltages internally, with a very fast rise time in the nanosecond range, with peak voltage levels of around 2 per unit. These very fast transient voltages do not cause a problem inside the GIS, as the duration of this type of surge voltage is very short, being much shorter than the lightning impulse voltage. Though an issue which can arise is, a portion of the very fast transient voltages can emerge from the inside of the GIS at any location where a discontinuity of the metal enclosure occurs, in locations such as insulating enclosure joints for external CTs or at the SF6-to-air bushings. Gas monitor system. Insulation and interruption characteristics of the SF6 gas will depend upon the density of the gas, at a minimum level of density which has been established by design tests. Pressure of SF6 gas varies with temperature, so a mechanical or electronic temperature compensated pressure switch is used to monitor the equivalent of gas density. Allowable loss in gas density. GIS enclosures are filled with SF6 to a density well enough above the density minimum for full dielectric and interrupting capability, that 5 to 20% of the SF6 gas can actually leak out before the performance of the GIS degrades. Gas compartments and zones. GIS systems are divided into separate compartments for the purpose of handling the gas, by the use of gas barrier insulators. Because of the arcing that takes place in a circuit breaker compartment, it typically has a gas compartment to itself. Gas handling systems are available to easily process and store around 1,000 kilograms of SF6 at a time. However, this process is usually impractical, due to the length of time needed. Therefore, larger compartments are subdivided into smaller gas compartments consisting of several hundred kg per section. Use of bypass piping to interconnect subcompartments. These small compartments may be interconnected with external bypass piping to create a larger gas zone for density monitoring. Testing requirements. Test requirements for circuit breakers, CTs, DTs, and surge arresters are not specific for GIS. Representative GIS assemblies having all of the parts of the GIS with the exception of the circuit breaker are design tested to show the GIS can withstand the rated lightning impulse voltage, switching impulse voltage, power frequency over voltage, continuous current, and short circuit current. Test standards. These specify the test levels and how the tests must be performed. Production tests of the factory assembled GIS including the circuit breaker cover power frequency withstand voltage, conductor circuit resistance, leak checks, operational checks, and CT polarity checks. Other components such as support insulators, VTs, and CTs are tested in accordance with specific requirements before assembling into the GIS. Field tests repeat the factory tests. Air evacuation and gas filling. Evacuation of air from gas compartments that have been opened is required once the system is sealed, filling with SF6 gas and control system wiring. Appropriate field tests are then completed. When the high-voltage GIS units are shipped as multiple, separate modules, the installation and testing of these units will take around 2 weeks per circuit breaker position. Lower voltage systems which were shipped as complete bays, and factory wired, can be installed considerably faster. The operational procedures of a GIS such as providing systems monitoring, control, and protection of the power is similar to that of an AIS, except that internal faults are not self-clearing, so rec losing should not be used for faults internal to the GIS. During a fault condition, the internal pressure will rise in the GIS's compartment as an arc heats the gas. In extreme cases, the internal arc will cause a rupture disk to operate or may even cause a burn-through of the enclosure. If this occurs, the resulting release of hot decomposed SF6 gas may cause serious burn injuries to nearby personnel. To properly protect the GIS system and GIS personnel, secure interlocks are provided so that the circuit breaker must be opened before an associated disconnect switch can be opened or closed, and the disconnect switch must be opened before the associated ground switch can be closed or opened. Inspecting circuit breakers. With the exception of circuit breaker equipment, for special use applications such as a pumped storage plant, most circuit breakers will seldom require an internal inspection. Likewise, most GIS will never require opening for maintenance. When circuit breakers are subjected to repeated tripping, they should be checked and repaired after 6,000 times of mechanical operation, while an interrupter should be overhauled after breaking 20 times of rated short circuit current up to 40 kA. Operational experience suggests that this maintenance regimen far surpasses the performance requirements.